Hello, this is Rick from MathX, and this is our fifth and final installment in our cool little ways to find the area of a triangle. Today, we'll be finding the area of a triangle using its circumradius. Now, for those of you who don't know what a circumradius is, don't worry, I'll get to that shortly. But the key thing to note is that this is a very important skill to know when trying to attempt higher level math competitions for high school and middle school. As competitions like AMY, ARML, and AMC 10 like to use this trick to throw students off guard who don't know this. So it's quite important to learn this trick. Now, here's the formula. A equals to ABC over 4R, where A is the area, A is a side length, B is another side length, C is another side length, and R is the circumradius. So it's quite a cute little formula. Not that much stuff to remember. We have a product of all the side lengths on top. We have 4 times the circumradius below. And we have that this is all equal to the area of the said triangle. Now there's a cool proof in this using either trigonometry or just pure geometry. But you can search that up yourself. Right now, I'm going to first explain to you what a circumradius is, and then maybe a couple cool tips and tricks to keep in mind when applying this formula. So, for those of you who don't know, you can generate a circumcenter by drawing several perpendicular bisectors in a triangle. So in this case, we have a perpendicular bisector on this side BC, a perpendicular bisector on this side AB, and a perpendicular bisector on the side AC, and take their point of concurrency as the circumcenter. And the deal with the circumcenter is it's the center of a circle that runs through vertices A, B, C of any given triangle. So the circumcenter of any given triangle is the center of the circle that runs through each of the vertices of said triangle. And if that's the circumcenter, then it's quite easy to see that the circumradius is just the distance between the center of the circle to the edge of this larger circumcircle. Because of that, there's several interesting properties that come up. First, the circumradius of a given triangle is the distance from the circumcenter to each vertex, because each vertex lies on the circle and all radii to the center are equal in length. So the distance from the circumcenter to A, and the distance from circumcenter to B, and the distance from the circumcenter to C, all these distances are equal. This point is equidistant from A, B, and C. And that's pretty good in geometry problems because you can exploit them similar to isosceles triangles with their equal sides. Furthermore, there's another interesting property. In this case, I already showed you the circumcircle of an acute triangle, and we can see that the circumcenter lies inside the triangle. But if we take the circumcenter of an obtuse triangle, this circumcenter would lie outside of the triangle, with the obtuse triangle being outside of the circumcenter. And the coolest property probably comes when we take a right triangle. As using a right triangle, we can actually use a lot of calculations given the circumradius of a right triangle. Because the circumcenter of any given right triangle is the midpoint of the hypotenuse. So even though it might look nasty to try to compute out the circumradius without this formula, in right triangles we just need to take half the length of the hypotenuse. And the diagram will look somewhat like this. Now the proof to this is really easy. Because a right triangle has a right angle, and because of inscribed arc theorem, this right angle will intercept an arc that's 180 degrees, which basically makes up half the semicircle. Since this is half the semicircle, that means that AC must be the diameter of this circle. And thus, O, which is the circumcenter, lies right on its midpoint. This can be really useful when dealing with right triangles and circles, as you could easily use this property to find certain lengths of inside a triangle, or find the area of a circle circumscribed around a right triangle with quite ease. You could also use this to verify that this formula works. Plug in some sides 3, 4, and 5, and check that if we apply 3, 4, and 5 as sides ABC, and 5 over 2, so the circumradius, as R, check if the area matches up. Anyways, enough with the circumradius and the circumcenter and all these cool properties. There's more, but these are the ones I felt that you should probably know. Anyways, without further ado, let's just get onto a practice problem so I can show you how you can use this problem to solve actual problems. So let's go do that. So here's a problem I found from the University of South Carolina High School Math Contest 1993, which I presume to be just another high school math contest, showing how this problem is prevalent in pretty much a lot of math contests, high school level. And this question isn't very long. It's simply, if the sides of a triangle have lengths 2, 3, and 4, what is the radius of the circle circumscribing the triangle? So the question gives us sides, and it wants us to find the circumradius, basically the radius of the circle circumscribing the triangle, which we've determined to be circumradius. So the first thing we should do is bring up the formula from our previous slide. Now, I kind of switched up the formula to match our needs. The original formula was A equals to ABC divided by 4R, but as the question clearly asks us for the circumradius, we can just swap out R and A using some simple algebraic manipulation. From here, we just need to use the sides that we already know to try to get at least the top part of it done. We can compute for the area later using Heron's formula, but we have to take the products of the lengths of each side, which the problem clearly tells us is 2, 3, and 4. Now, 2 times 3 times 4 is simply 24, so we already got the numerator part of this equation. Now we just need to find the area using Heron's formula. Now, if you don't remember, Heron's formula basically takes the square root of the product of the semiperimeter times the semiperimeter minus the first side, the semiperimeter minus second side, and the semiperimeter minus the third side. And if you need to revise that formula, you can go back to a previous video, because I made a video on Heron's formula, and we used it to solve a nice AMC8 problem. But for now, just take the semiperimeter by adding up all these sides, and you'll get a length of 9 and divide it by 2. And then subtract 9 by 2 from each of these sides. 9 by 2 minus 4 will give us 1/2. 9 by 2 minus 3 will give us 3 over 2. And 9 by 2 over 2 will give us 5 over 2. So now all that's left is to simplify this out. So we can take a 4 from the denominator, and we could probably take at least 1 3 out as well. So by taking this 3 out and taking a 4 out, we get left with 3/4, and since 1 3 and 1 5 remain, 3/4 times root 15. So we have our A part of it using Heron's formula, and we have our ABC just by multiplying 2, 3, and 4. So we just need to multiply it by 4 and then divide these two parts properly, and we're going to get the circumradius of this triangle. So multiplying 4 with both sides, instead of 3/4 by 15, we're going to get 3 times root 15. So our entire expression comes out to be R is equal to 24 over 3 times root 15. Now, obviously that's not an answer here, because 24 and 3, these can be simplified down. So 24 divided by 3 will give us 8. So the true answer is 8 over root 15. So right now, we just solved a high school level math contest problem just by using the simple formula. Not even being that creative with it. We just plugged and bash. We had to use a little Heron's formula, but hopefully you remember that from our last video. Showing how this problem is, showing how essential this formula is to know in solving math competitions. And it's not even that hard to remember. A, or R in this case, is equal to ABC divided by 4R, or A. It depends which one you want to find. So that's pretty much it for finding the area of a triangle using its circumradius. But before you leave, I have one cool trick that I just want to show you. So one final bonus method in computing for the area of a triangle is computing for the area of a triangle only using its altitudes. Now, I've been doing math competitions for a little bit of time now, and I'm not going to say I'm the pro at this, but I'm pretty sure this formula is nearly useless. So, here it is. It's really long, and there are a lot of components to it. We see that there's an H, a big H, and then there's HA, HB, and HC. So, this is what the diagram will look like. And it's kind of clear. So in this formula, HA, HB, and HC just take the place of H1, H2, and H3. They're just heights to respective sides. Because remember, every side of a triangle has their own respective height. And you can find that height by just dropping the perpendicular from the opposite vertex. So we found out what the HA, HB, and HC were in this expression, but we don't know what big H is. And basically, big H is just kind of like the average of the reciprocals of the height. Now, these altitudes will all intersect at this point known as the orthocenter, but that doesn't really play an essential role into this formula. This formula is just fun to know for trivia, but on a competition, don't expect it to come in use, because very rarely will they just give you a problem in which you just have all the heights. But if you do have all the heights, and you can recall this formula, well, that's great for you. You solved another problem that most people can solve. So that's pretty much it in my series in which we find the area of a triangle. We've gone over several different methods. In the first episode, we went over the basic methods that hopefully everyone knows, but we took an interesting twist on it. Second episode, we used Heron's formula, a really cool formula that allows you to find the area of a triangle only using its side lengths. Third time, we used a little bit of trig to find the area of a triangle with an angle and two sides, which I like to refer to as SAS area. Fourth video, we used the classic formula, area equals radius times semiperimeter, where radius in this case was not circumradius, but in radius. And that formula really helped us solving us AMC8 number 25. And in this last video, we went over not only circumradius, but this little cool trivia kind of altitude method. So, as you can see, find the area of a triangle is not as clean cut as it clearly seems. It's not hard, but you can be creative with it. You can have a lot of fun just trying to figure out all the different ways you can find the area of a triangle. And to succeed in most math competitions, you can't just know one or two. You have to know at least like 3 or 4. Maybe not this one, but the other ones. Area equals radius times semiperimeter, or SAS. These ones will really help you on a math competition.